The main idea of this lecture would be to see how we can relate whatever we have seen in this school, basically the PM, the PN, the tails, with this EOB formalism that we have. But before going into the details, let's do a quick revision of what we have seen so far. So we said that PN has to be resummed. And then we motivated EOB with the main idea of this was to combine test mass results with the PN results, attach the ring down, and calibrate with numerical simulation. When we were combining the test mass results with the PN results, we said we can split this, combining these two things into 3 building blocks. The conservative piece, radiation reaction, and gravitational wave modes. In the conservative piece, we obtained a map. We obtained a map which related the real, which was the PN results, with the effective one-body Hamiltonian. And this effective one-body Hamiltonian is basically a deformation of the Schwarzschild results. And in the tutorials, we have tried to focus only in circular orbit limit, where this B will disappear, Q will disappear, because that's what we wanted to see in simplest scenario, that H hat effective remains simple. So we calculated what this A potential would be. And in radiation reaction thing, we said we need to also resum radiation reaction force. There were 2 approaches. One was the approach of the Iyer and Satyaprakash DIS approach, and the other that we discussed mainly was resumming the gravitational wave modes. And the gravitational wave modes are related to the flux and the luminosity like this. So if we have resummed the gravitational wave modes, in some sense we have also resummed the radiation reaction force. And then we added all this information into the equations of motion and obtained the waveform for the in-spiral plunge part. And then we attached the ring down to it. After obtaining this full analytical waveform, we calibrated it with numerical relativity simulations, because all this results that we have are based on the PN information, which we know only up to a finite order. And then we said that with increasing signal to the noise ratio and upcoming detectors, we need even more precise waveform templates. So if everything is based on PN, and PN, we know only up to 4 PN exactly, and 5 PN partially, do we need to wait for all PN orders to be computed or higher PN orders to be computed to know something in EOB? Or is there something else that we can use to inform this EOB Hamiltonian? And that's how we motivated the tutti frutti approach that we discussed yesterday. Which was basically taking the information from PN, PM, gravitational self-force, multipolar Postman-Minkowski, and numerical relativity simulations to obtain something here in the H hat effective. Then we said there are 3 steps of doing the tutti frutti approach. The first was to separate the local piece from the non-local piece. Because we said that the computations in 4PN becomes complex starting from 4PN. because of a conceptual shift, which was addition of tail. So you want to separate out the tail effects and the instantaneous effect, which is acting at the same instance, and hence the local effects from the non-local piece. This we could do using MPM. So basically, we can obtain this non-local piece for free, even though we don't have higher PN order results from the post-Newtonian formalism. Then we said we use the information of gravitational self-force because it's an expansion in mass ratio, which can be related to an expansion in nu. And if we rearrange this A potential, we can write it as A self-force with exactly in U, which is the radii 1/r, and nu being the symmetric mass ratio. So if we have something here, we should be able to inform the ASF metric potential term, and hence able to obtain something higher order in A, which was not even available from the PN side. And the gauge invariant variable, because we want to always work with gauge invariant variables. The gauge invariant variable used or considered here was redshift. And in yesterday's tutorial, you computed the 4 PN contribution coming to this A potential, which was A5, with the information from the redshift. But we know that even from PN sense, the state of the art is complete 4 PN results. So whatever we have obtained here from the self-force result, it should match with the 4 PN result computed from the PN sense. You might have checked that up to 3 PN, that's the case. The 3 PN results obtained from the PN sense and from the redshift are matching quite well. Whereas at 4 PN order, there is a little subtlety that the result that you compute from redshift, basically the GSF computation, and the term that you compute from the PN results, they don't agree very well. There is some error, and this error is 30 times larger than the error on the numerical error bar from the numerical error bar in ZSF. So it says it tells us that we need to go to higher numerical accuracy in self-force computation to be able to obtain the A5 better. And it also tells us that we need to do the matching between the results from various schemes. At least in the region where there is an overlap. To precisely know what we are computing is exact or not. The third step that we didn't discuss yesterday was scattering, or let's say the PM computations. And in PM computations, scattering angle is the gauge invariant variable. Which we will denote by chi. This is the gauge invariant variable in PM computations because PM computations are naturally suited for hyperbolic encounters, and hyperbolic encounters are nothing but just flybys. And these are the kind of computations I think you have seen in today's or in the morning lectures of this week. And then we said this PM computation and PN computation has an overlap, and we saw a grid that the PM computation matches with PN up to a particular order. Let's see that again. Since the PM computations only assumes weak gravity, so we know results up to all velocities. So it's saying that we know the full 1 PN information if we have the 2 PM results, and vice versa. If we have 1 PN information, we know part of the 2 PM results. So let's focus on the 1 PM and the 2 PM results and see how we can use that to inform something in the how we can use that to inform something in the A potential or B potential. This is the 1 PM result of the scattering angle. And this is the 2 PM result. Where gamma is the Lorentz factor, which is 1 over minus square over c square. So if you do the expansion in if you want to do the expansion in small velocity, basically you are expanding these Lorentz factor, and hence you will be able to obtain the PN results that we were saying. And this PN result should match with the PN results we have from the post-Newtonian calculations. And B is the impact parameter. H is the effective energy. Yes. So we have these. And we also mentioned yesterday that this Lorentz factor is actually, if you look at this equation, and if you look at this equation here, it shows that in hyperbolic encounters, gamma is the same as the effective one-body energy. Gamma is in some sense. And we note here that this chi1 PM and chi2 PM are independent of nu, so they are not dependent on the symmetric mass ratio. And we also saw a few in one of the lectures that if we do the expansion of A as normally in PN sense, we saw that this was 0. This A3 was only linear in nu, and this A4 was also linear in nu, despite the fact that PN computations are not linear in nu. They depend on nu square, nu cube thing. So the fact that this is 0, this is linear in nu, and these two things are independent of nu suggests that there is some hidden structure. Which we will discuss shortly. But let's see how we can use this chi1 PM, chi2 PM information to obtain something here in A potential. Now we note that the PM computations or the scattering angle computations are for hyperbolic encounters, so we cannot consider a circular orbit limit, implying we should be able to obtain everything A, B, and Q, and we are not able to isolate the A potential as we could isolate in the GSF computations. And the relation between the scattering angle and the effective one-body metric is this, where PR is the radial momentum. And now from this here, this equation here, we should be able to invert this to obtain PR in terms of the H hat effective, A, B, and Q. We said that this H hat effective is nothing but just the Lorentz factor. So we know this point. And A, B, and Q is something we can expand like this. We can consider some ansatz, and then we can compare order by order the scattering angle computed from the PM sense and scattering angle computed from the EOB Hamiltonian, and see what these A, B, and Q are. So at 1 PM order, it's just proportional to 1 over B, and this is 1 over B square. 1 over B square, so it's saying that it is 1 over, it's U and U square kind of a term. So we have everything to all orders in velocity in U and U square. So what can we inform? First thing is we can check that what this A2 U square would be from PM computations, and something from U square as well, to see what we can inform only from these two computations. Let's see the ansatz again. All these results are known from the PN sense, and we want to see something here. Similarly, for B, we have the ansatz, which is all of this is known from PN. We want to see something here. Very small. Sorry. Which one? Is it the B or the Q? Q. So, and there are coefficients like Q1, Q2, Q3, Q4, Q5, and Q6. These terms, again, we know from the PN calculations, and we are looking for something here in the 5 PN computation. We said that the 1 PM and the 2 PM computations are exactly known in U and U square to all orders in velocity. So this suggests that the term that we are able to obtain from the 1 PM and 2 PM results is actually this piece of the 5 PN computation. So we have obtained PR8. From PM, and we have verified this A2 and B1 and B2 term and this Q1 term from the 5 PM, from the PM computations when doing the expansion in PN. And the reason this was PR4 is we said Q enters only at 3 PN order, so it has to be at least quartic in P. And U is because of the dimensional analysis that we saw in lecture 2. And for simplicity, we were focusing on something which would be simpler in circular orbit limit. Basically, when PR goes to 0, I would want Q to go to 0. That's why I only considered PR, but one can consider another choice where we don't have PR, but we have P5 as well. But where? Here? This? It's Q3 is like the coefficient of this term. So it's just a coefficient. It's Q1 times this, because there would be a coefficient. It's just, it doesn't come without any coefficient. So it's just any number, any coefficient that you can choose. So now I said that there has to be some hidden structure in this PM computation, and there is some hidden structure in this series as well. So what is this hidden structure? So the hidden structure is called polynomiality. Polynomiality in symmetric mass ratio nu, because that's what we were considering. It was a polynomial in nu, where this was linear in nu, this was 0, this was also linear in nu. And similarly, it's nu with independent of nu, so it's a 0 order term if I consider some polynomial in nu. So the statement of this hidden structure or polynomiality in nu says that the scattering angle cannot be an arbitrary function of nu, but it has to depend on on some structure. So how is this scattering angle computation done in the first place? The scattering angle computations are done using EFT computation, so basically by considering Feynman diagrams. And this structure, this diagrammatic representation of the PM results that we computed here restricts the polynomial in polynomial of chi, like basically saying what could be chi, how chi could be dependent on nu. So the statement is not arbitrary function of symmetric mass ratio nu, but it depends on the diagrammatic structure of the diagrams. So it's not an arbitrary function of nu, but it is dependent on the diagrammatic structure of the PM computations. Basically, the Feynman diagrams is the polynomial of chi dependent on. And the answer is that chi n, where n denotes the PM order, is a polynomial in nu. So basically, it has to be like this, where this is the smallest integer. So it can only be a function of nu of this polynomial of this degree. It cannot be a polynomial of any degree. So what does that imply? If I consider some PM order and see the degree of nu, what I obtain is at 1 PM order, it is a polynomial of nu to 0. So it is independent of nu. At 2 PM order, it's also independent of nu. At 3 PM order, it can only dependent linearly on nu. At 4 PM order, it can linearly dependent on nu, and so on. This verifies what I wrote here, that chi 1 PM is not dependent on nu, and hence it can completely be determined from the Schwarzschild results. And is oftentimes called as probe limit. And now we go back and look at this grid structure. What we are saying here is, if we know 2 PM results exactly, we should be able to know the 1 PM results completely. We just saw that the 2 PM results, up to 2 PM, everything is independent of nu. So we do not expect any nu dependence here at the 1 PN order in A2. If it cannot dependent, if it cannot dependent on nu, it implies it has to be 0, because this is the exact Schwarzschild result. Schwarzschild result cannot be modified because it's the exact solution. So this A2 has to be 0 like that. And if we look at these results, which are 3 PM and 4 PM results, and if you go back and look in the grid again, we say that 2 PN is completely known if we have results up to 3 PM in the scattering angle. And 3 PM result is only dependent on nu, which suggests that this A3 can only linearly dependent on nu. And there cannot be any higher new terms in this A3 2pn result of effective metric. So cancellations are a good thing, but cancellations have a hidden structure in it. And now if you want to prove this polynomiality structure, it doesn't come just like randomly. To prove the polynomiality, let's look at the diagrammatic structure. In your lectures of this week, you studied the impulse calculation or the transfer of momenta at the leading order, which is basically this equation here. And the transfer of the momenta or the impulse is directly related to the scattering angle because it checks how the motion is different from the straight line. And the relation between the scattering angle and the impulse is where PCM is the center of mass moment at infinity. And this is nothing but just the magnitude of the impulse that you have computed, which I denote as m of chi. And this center of mass momentum has to be mu times something. And this m1, m2 is going to give us mu times mass. And the dimensionless variable or the dimensionless scale in the system is gm1 over b or gm2 over b. So gm, where m is the total mass, becomes the scale. So it suggests we have to take out this as a common factor from all the higher order terms. Let's consider higher order terms now. This is the Feynman diagram at leading order. This is the next leading order computation. And these are the higher order diagrams that will enter in the computation. So now let's write the structure of this magnitude of the impulse. The magnitude of P, as we said, we need to take this as a common factor, would be some contribution coming from one diagram, let's say one exchange. Since the dimensionless scale is just gm1 over b, so there could be another. These would be the results coming from this diagram. And then from these, what could be the possible things are m1 squared terms. This could be the structure of the magnitude of the impulse, and the structure is such that from here we have only m1, m2 because there are only two particles. Here we have m1, let's say these denotes particle 1 and this is particle 2. we can have m1, m2 square, m2 square, m1. From here, we will have m1 square, m2 square, or there could be diagrams like, which would be m1, m2 cube, and there would be an inverse of this as well, which would be m1 cube, m2. And if I factor out m1, m2, so this could be the only structure that could be present of the magnitude of the impulse. Now, these diagrams have an exchange symmetry, like, for example, what I mean by that is, if I change one particle by 2 and 2 by 1, these results should be the same. So basically, it's saying Q11 is equals to Q22. Here as well, these two terms will be same. Q21 would be the same as Q12, which implies that these terms, this term, is only dependent on one mass, and anything which is dependent on only one mass, that's the test particle case or the probe limit case. So we can obtain these expressions or these things directly from the probe limit. Or the Schwarzschild results, and that's what we obtained here as well, that this chi2 is independent of nu, which means it is direct the Schwarzschild result, and that's what we obtained from the structure of the magnitude of impulse. Let's look at the second term. The second term has Q11, Q22, which are only dependent on m1 squared and m2 squared. Again, because of the symmetry, these two terms are equal. Since they are only dependent on one mass, they can also be directly obtained from the probe limit. But as soon as we go to the next terms that enter here, which are Q21 and Q12, they start containing mixed terms like M1, M2. These cannot be obtained from the Schwarzschild results directly. And this M1, M2 is mu m square in terms of the symmetric mass ratio, suggesting that the 3pm result has a degree 1 in nu. And that's how we can derive the polynomiality of chi. And this directly translates to the polynomiality in the A potential, B potential, and Q potential of the effective one-body Hamiltonian. So from this, we saw that we can use PM results to inform something in the EOB metric potentials. We can use GSF results to inform something in these potentials. We can use MPM formalism to obtain something in these potentials. So it suggests that EOB is not just one single computation which relies on PN only information, but it is a powerful tool. So we saw that MPM can inform A, B, and Q. GSF can inform A, B, and Q, the metric potentials of EOB. Scattering can inform A, B, and Q, all in EOB, implying EOB is not one computation. Which only relies on PN. Because if you remember, everything that we built here, which was splitting into conservative ARA, radiation reaction, and gravitational wave modes, was starting with the PN information. But from here, we said that we can also use MPM, GSF, and chi, the scattering angle, to inform these EOB things. Which suggests that EOB is a tool which uses everything from everywhere that we know in perturbative sense. So it uses results of PN, which was traditional methods. we saw that it can use the results of PM that you might have computed in morning lectures. This you might have computed in last week's lectures. It uses MPM, which is in some sense separating out the tail effects from the local piece, which you also have studied in last week's lectures. Then it can also use gravitational self-force results. We also saw that when we attach ring down to it, we use black hole perturbation theory results. So it's also using black hole perturbation theory results. It also uses NR to give us a waveform which is reliable, fast, compared to NR simulations, because NR simulation might take a lot of time and is quite expensive. Accurate. And the current state of the art of the EOB waveform templates are such that the mismatch between the numerical relativity waveforms and the EOB waveform is 10⁻⁴, which implies that the EOB waveforms are quite accurate. And it is a powerful tool which can use information from every place in perturbative sense. And in some sense, it's the tutti frutti thing, the EOB. And now to relate it to what you might have seen in the lectures 1 of last week. So in last week's first lecture, there was a discussion about a plot which related the compactness or the field strength with the mass ratio. And then we discussed that there are these perturbative schemes are valid in different parts of this parameter space. For example, here I'm considering 0 and 1. So self force is valid here, like GSF. PN, PM. I did something wrong. PN, PM are valid here. And our results are somewhere here because they are for comparable masses and high compactness. And then we also have some results from black hole perturbation theory. I think something like PN, PM. And this is self force. And here we have black hole perturbation theory results. But there is some region where none of these perturbative techniques or even numerical techniques go. And EOB is trying to even capture this regime where none of these perturbative techniques or exact solutions are available. So saying again that EOB is powerful enough that it can take information from everywhere, give us a waveform, and can even probe the parameter regime, which cannot be probed entirely by self-force PNPM, NR, or BHPT separately. So this is what I wanted to show about EOB. In the first lecture, I said that we can also use EOB or PNPM computations, not only in GR, but also in theories which are beyond GR. And we focused everything here on black holes as the compact object, or neutron star as the compact object. Yes. Yes, so it's not a limitation. It's a good thing about EOB that it can even probe the regime which cannot be probed by anything else. Because it's not a perturbative scheme which is relying on something one particular. It also uses self-force. It means it can be extended here. It uses BHPT, it can extend here. PNPM, it means it is valid here. reliable with NR, it is valid here. So there is no reason for it not to be valid here. On EOB, the limitation is that it depends only on, it depends on these perturbative schemes we said. So the limitation, whatever the limitation we have here in terms of whatever order we know, is the only thing that we know in EOB. But one can then say we calibrate with NR, so we can obtain the higher order corrections from numerical relativity simulations. That's because we don't have results from the analytical side of PN, PM, or self force. Once we have those results, we can map it to EOB. And the other limitations like EOB, in EOB can be the leading order radiation reaction starts at 2.5 PN. The radiation reaction squared becomes 5 PN. There is an intermixing here. One doesn't know how to like separate it out completely. There is this problem. The other thing could be spin, as for example, spin is not very well understood in EOB sense. When we derived this energy map, what we said was we are considering the total, we were saying that the total linear momentum P is equals to 0, but there could be recoil as well. There could be situations where there is recoil. We started everything with 0 recoil. So how to incorporate recoil? If it is quite small, then we do not care about, which is what we expected in the binaries that we have observed so far. The recoil could be another thing. So there are still open problems, but the key idea is that EOB can also probe the region which cannot be probed by anything else. Yes. Yes, so basically you say that this H effective is H orbital plus H spin orbit, for example. Yeah, you just separate it out like that. Okay. So I was saying that EOB is powerful, and we can use it to even probe the region that cannot be probed by anything else. And just to quickly mention, by using this tutti frutti approach, what we can obtain was the full 5 PN Hamiltonian modulo only 2 factors. And at 6 PN, we know the full Hamiltonian modulo 4 coefficients. And when I say this Hamiltonian, I'm talking about the real Hamiltonian as well, because using this energy map, if you know this, you can find what the H real is. So that's what I was saying about EOB, that it's a powerful tool. Now, if one would also like to probe maybe something else which is not GR, because everything that we did so far was in GR. Compact objects such as black holes and this is what we focused on so far. But because of the observationals from cosmology side or theoretical inconsistencies, one would expect that there should be something which is beyond GR. And there could be other particles or other compact objects as well, such as boson stars. Roca stars or anything else. Like exotic compact objects. And why do we care about building waveform models in beyond GR or exotic compact objects is the same reason that we have the signal to noise ratio is continuously increasing. We expect more detectors, so there is a possibility we may be able to constrain these beyond GR theories or maybe rule out some of them. We may be able to find some new particle which is beyond standard model. Suggesting that GWs provide a wealth of information which we can use for either this or a mixture of this. And for that, again, we need precise waveform templates to be used by LIGO for the detection purposes as well as parameter estimation. And we also need these waveform models for detection purposes because we want to remove the stealth biases in our detection. And stealth bias means that if we have only a waveform model based on particular theory, then we are only bound to detect the waves originating from that theory only. So to even remove stealth biases. Or minimize, let's say. So these are the particular motivations of building waveform models in beyond GR or exotic compact object theories. Now, when we say beyond GR or we say exotic compact objects, there is a zoo. There is a zoo of beyond GR theories. Because we can modify GR as we like. We can add extra degrees of freedom by adding extra fields to the system. That is not only the graviton, but there could be any other field like scalar, vector that can be propagating. We can modify it by going to higher dimensions. We can do a lot of things in beyond GR. Similarly, in exotic compact objects, we can add a particle like a bosonic field. The mass of the bosonic field is not the same as what has been observed for standard model particles so far. So we can have various things here, or we can also have like cosmic strings, which would be the beyond standard model particles as well, made up of axion fields now. So how do we choose which beyond GR theory we should be studying? We want something which is simple enough. Simple enough to do the calculations because we want to do the calculations in PN, PM, self force, black hole perturbation theory or MPM. So it should be simple enough that we can do computations. But it should also be interesting enough. That there is new physics to learn. These are the two conditions from the computation point of view, but the theory should be physically viable as well, meaning that there should not be any extra ghosts in the system. So it should have no ghosts. The theory should be well posed, which means that if I give some initial condition, the solution should exist. The solution should be unique. And if I evolve that system, the system should continuously evolve given some initial conditions. And it should be motivated from some we should be motivated to explain something like some discrepancy that we observed from cosmology point of view or from theoretical models. So one simple class or one class of such modified theories would be just addition of a simple scalar field. So in addition to the metric G mu, so in addition to the metric G mu, we also have scalar field now. So this is a simple class that we can study where we have only scalar fields as propagating. And that could be a beyond GR model. This can be motivated from cosmology point of view if you want to explain inflation, for example, dark energy or dark matter. So from cosmology, inflation could be one motivation. From theoretical models, they can also be inspired from string theories. Like Kaluza-Klein kind of theories, where you consider higher dimension, but that higher dimension can be compactified such that it behaves as a scalar field. So we can find motivation for such theories, for scalar tensor class of theories, both in cosmology as well as string theories. And in this scalar tensor theory contains a lot of theories, for example, Hordinsky gravity theories, where you consider higher derivatives, Einstein scalar Gauss-Bonnet, and it's a very big class. So what can be the simplest case that we can study here? It would be just a massless scalar tensor. Where the scalar field that's propagating is massless. And now one might ask, why do we want to study these massless scalar tensor theories? They are well constrained by binary pulsar observations. For example, DEF, Demour-Esposito-Farasik kind of theories are very well constrained here. But why still we study these theories? Because they are simple enough. It helps us in understanding how the structure of modification would look like if one wants to go beyond GR. So it helps us in developing tools. For beyond GR theories. And a lot of theories which are in scalar tensor class, they reduce to massless scalar tensor theories in some approximation or up to some post-Newtonian order. For example, to certain Pn. For example, the Einstein scalar Gauss-Bonnet, or called as ESGB, is same as massless scalar tensor. I would write it as SC everywhere from now on. So it's same as massless scalar tensor up to 2Pn order. So everything that you compute here is also valid for Einstein scalar Gauss-Bonnet. Then there are other class, like for example, dynamical Chern-Simons. Which reduce to massless scalar tensor up to 5Pn. So these class of theories provide a good baseline even to study even more complicated theories like Einstein's Gauss-Bonnet or dynamical Chern-Simons. So these could be the motivation of studying massless scalar tensor theories. Now what happens in these massless scalar tensor theories? But before going into that, let's look at the action, how the action modifies. So this is the action of a massless scalar tensor. Here we see that the metric is minimally coupled to the scalar field. So one would expect there is nothing new happening here. But the scalar field is coupled to the metric via matter. So the matter action changes, which gives the dynamics to the scalar field. So there could be some interesting things happening, especially for neutron stars. Or if one adds higher order terms, there could be some effects for black holes as well. But if we instead of writing this theory as a non-minimal coupling of matter with the scalar field, if we try to write it as a non-minimal coupling of the scalar field with the metric, what we get is that this is equivalent to so basically the non-minimal coupling between matter and the scalar field has now been shifted to the non-minimal coupling of the scalar field with the metric, which suggests, because here is 116 pi g, this suggests that the Newton's constant is not a constant anymore, and it has become an effective constant, or it has become some effective g. When one goes from gr to the scalar field. And if it becomes g effective, it means that the compact objects formed in the scalar tensor theory would depend on the scalar field, meaning that the size and the internal gravity of the compact objects, the size and the internal gravity depends on the scalar field phi. And if we want to now write the point particle action of this scalar of compact objects in this scalar tensor theories, what we would try to do is we will try to skeletonize it, because we need to take into account the effect of phi as well. So now the matter action, instead of it being minus m d tau, where m was the constant in gr, now it becomes with mass being dependent on phi. If when mass becomes dependent on phi, we can do a Taylor expansion of it, which becomes m constant plus evaluated at phi some value, and there is delta phi, blah, blah, blah. And if we want to rewrite it like this, now these terms, which we define as the coefficients or the parameters in scalar tensor theories, which we now call as SC parameters, now they will encode the dynamics in the Lagrangian. So now the Lagrangian will also depend on these parameters, in addition to it being dependent only on the masses. That's what you do, right? So if you have G menu, that's how you do the computations. Here, yes, it can be. It's just that the G menu will not be Schwarzschild, it would be deformed from Schwarzschild. but the Minkowski is just Minkowski. It's the gravity coupling with the scalar field, or otherwise you can say here that the scalar field is just propagating. It would just become Einstein, or just it will be just Klein-Gordon, for example, if you have flat space-time. Okay, so I was saying now this is going to encode the information of the scalar dynamics in the Lagrangian. Now, if we look at this matter action more carefully, we said that this matter action is what determines the propagator attached to the world line. And we said that we can write this matter action such that it is quadratic in velocities. When we were studying some subtleties about the point particle action, we wrote it as like G mu nu times of U mu U nu with M in GR. And we said because of the presence of linear in G mu nu, there was only one single point particle function, which was this. And hence we only had one propagator being attached to the world line, and there were not multi-propagators attached to the world line. However, when we consider the scalar tensor theories and we write it in this quadratic form, this m not being a constant implies that we might have, or we will also have more propagators attached to the world line. So it's making the calculations a little bit more tough compared to the GR case. So we have so this in scalar tensor implies where u was the for velocity defined as dx. So we said that now there is m phi as well, implying there is not only this one point function for graviton, there will be one point function corresponding to the scalar field, which I denote by dashes, but there will also be now multi-point functions attached to the world line, making the computations difficult. But since we are considering only massless scalar field, what it means is the propagator of the massless scalar field is 1 over k square, and the propagator here is also 1 over k square with some tensor. It suggests that the master integrals that you obtain here would be the same as the master integrals you obtain here. Though the computation is hard because you have to keep track of more diagrams, but in some sense it's easy because you can directly import the information that you have here of master integrals into the information here. So one can do that, and this way we can obtain the PN PM results. If we have the PN PM results or self-force result, we can do the similar game of knowing something this side and obtaining something this side for the scalar tensor theories. And this is mapped to the EOB Hamiltonian in scalar tensor. So this we can do directly, but what does working in scalar tensor also imply? Like what kind of a physical effect that you can observe? Because that's what I said. We not only want a theory which is simple enough, but we also want a theory which is interesting now. What are the physical effects? Which then also translates to the computational effort or computational effect. The physical effect is now there is a scalar field propagating, which implies there would be scalar radiation as well. In addition to the tensorial radiation coming from the gravity, there would be scalar radiation. Scalar radiation starts at a lower order than the gravity case. Basically, there will be dipolar radiation also in the system. If the system has dipolar radiation at a lower order than the quadrupole radiation in GR, what we expect is that the tail effects will start at a lower order. So they start at 3 pn order instead of it being 4 pn, as we were saying here, that when you separated the non-local piece from the local piece. So one has to start separating the A potential into A loc plus A non-local. At 3 pn itself. It's minus 1 pn. Yes. 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 So, and it can be shown if you start with the metric in that theory that way. So we expected dipolar radiation, tail effect start at 3 pn, the potential, the EOB metric potential, now you have to start splitting at 3 pn itself. But what does this dipolar radiation imply? It implies that there is an extra channel of radiation in the system now, which is the scalar radiation, suggesting that the two compact objects in scalar tensor theory would merge faster compared to GR case. We can't observe the scalar radiation. That's true. Yeah, this is what we are saying as well. Now it's also leaking from the dipolar or the scalar part. No. It can, like, if the parameters are such that it, instead of being, it's not gained, but it's, let's say, in some sense accumulated. That can possibly happen, but we haven't observed. Like physically, that you would not expect. You would only expect that there is some leaking or radiation being. So we said that there is radiation now from the dipolar side as well. So one expect faster mergers. Compared to GR, which implies that the frequency that you computed of ISCO in scalar tensor theory would be larger than the frequency that you compute for GR. If that's the case, then it will introduce some sort of a phase shift in the waveform. And this dephasing effect can be observed dephasing can be observed from GWs. And since this dephasing is dependent on these body parameters that you are considering here, like alphas and beta, etc. So we are saying basically if you observe the dephasing, you are putting constraints on these alphas and betas. So you are putting or you are constraining your scalar tensor theories or any other theory, for example. Constraints. On scalar tensor parameters. Now, the current state of the art is ESGB waveform models. By the AEI group. Late 2023. So it's quite a recent development where they have used the PN information up to 3 PN order and computed these A2, A3, and A4 corresponding to ESGB corrections. And one thing we note when we do this correction is this A2, which we expected or which we said would be 0 in GR is not 0 anymore, but it is not also dependent on mu. The reason why it's not 0 anymore is because it's not short-shell black hole anymore in ESGB, and the black hole in itself is modified, where the correction corresponding to the scalar field in the black hole metric is like 1 over r square. There is no reason for it to be 0 in scalar tensor or ESGB kind of models. So I was saying that the state of the art is 3 PN results. And since we are considering scalar tensor corrections or modified gravity corrections to be small compared to GR, so we add everything the scalar tensor corrections or ESGB. On the top of the GR results already. So everything is the baseline GR. On the top of it, you add the scalar tensor correction. And that's how they have. Yes. Yes, exactly. So it's like, I said there are scalar tensor parameters alpha and beta. So it's like beta minus some alpha. So I was saying that since the scalar tensor corrections are small and they are added on the top of GR, and the state of the art is only the 3 PN results and with all the information on ESGB, with all the information from GR, like the 5 PN information that we have for a potential from GR is considered as it is, and 3 PN results here. For the radiation reaction, the state of the art is only quasi-circular information, and that too only up to 2 PN order. And from these waveform models, it has been observed that the merger is faster, which is what expected, which is what we expect physically. And then this waveform model was in particular used to put constraints on the ESGB coefficients or the ESGB coupling constant. And that's the best constraint that we have from gravitational wave observation. Constraint. ESGB coupling constant. Best so far. Apart from this waveform model, there is also another waveform model. So this is AEI group. based on SUB-NR. There is another waveform model by Torino group, which is based on the other variant of EOB. And the difference between this model and this model is there are also tide effects, tides corresponding to scalar field. Are added also in this effect, and there is 3PN information for ST-ESGB Hamiltonian and the quasi-circular information for the waveform and the fluxes up to 2PN. And this has been used for binary neutron star configurations. And this has been used for mixed binaries like black hole neutrons, but without any tidal information from the scalar part. So that's what we see. I said that the ESGB or the scalar tensor corrections are small, so they are added on top of GR corrections. But this might not be always true. We might expect and other interesting phenomena where this beyond GR being small compared to GR is not valid anymore. One such thing in ESGB or scalar tensor correct kind of theories is spontaneous scalarization. So what does spontaneous scalarization mean? It's like a phase transition that this neutron star, which is surrounded by the scalar field, develops a very high or a very large scalar charge, breaking this simple thing of fast merger or like simple expectations that we have, or basically breaking the weak field results. Yeah. This is scalarization is like a phase transition. Developing large scale transition. This spontaneous scalarization can happen for the isolated system as well. In addition to spontaneous scalarization, there could be another interesting thing that can happen for binaries, which is dynamical scalarization. And it is phase transition happening because of the presence of the secondary object. In binaries. And one such phenomena of dynamical scalarization was observed from numerical relativity simulations, where one considered two black holes with opposite charges, and they saw that there was a flip of the charge. So for example, they started with like M1 alpha 1 and some M1 and the scalar charge being minus alpha 2. After some time, there was a charge flip, so it became M1 minus alpha 2, M1, M2, alpha 1. Something like this happened, which is not an adiabatic thing. It's like a phase transition, non-adiabatic. And this is something that cannot be captured when we consider ESGB to be like just small corrections on the top of GR, because everything here is considered adiabatically, that it's just a small correction, and the waveform is modified only in some small sense. One needs to see how one can add the evolution of the charges as well, so that it can capture this non-adiabatic behavior in the EOB waveform models. But that's still a work in progress. We studied that in GR there is a lot of progress. We have eccentricity incorporated, we have spins incorporated, we have tides incorporated. But in ESGB or scalar tensor, the information is quasi-circular up to 3pn. So we need to develop this model to be even better to break degeneracies, because this scalar tensor effect that we said is a fast merger can also happen because of the presence of tides, can also happen because of the spins. Anything can happen, like there is this is degenerate. With spins, with tides, and other physical effects that can enter into the system. So we also need to develop ESGB or scalar tensor waveform models for eccentric orbits, and spin orbits, spin information, tidal information, and other things. We need to add eccentricity because tides has already been added. Spin orbit is a work in progress, or spin. We don't have much information from the PN or PM side, so we cannot do much about adding high spin information in the EOB model. But eccentricity is something that we can capture, because we remember that E of the system, which was R dot FR plus phi dot Fi. E of the system is this. On the top, we also add E short. And this is equals to the energy flux computed at infinity in the PN sense. We have this information. And this flux is nothing but computed from the source multiple moments or the radiative multiple moments that we saw yesterday. So this information we have, we can compute this. Hence, we can obtain the FR, Fi, or E short for ESGB or scalar tensor waveforms. There are results known up to 2pn for eccentricity here. And this just means because of the presence of scalar radiation or the dipolar radiation, all these things start at the lower order, and it can be split as like only computing the scalar part and computing the tensorial part. I also mentioned when I was talking about the short terms that these are the total derivative terms. This can easily be seen when you just consider the dipolar radiation, because dipolar is easy to handle. So there the radiation force is nothing like A dot, where A is the acceleration, which is the third derivative of the dipole moment. And the E dot is nothing but force multiplied with the velocity. When you write this in terms of the multiple moments, you can write it as d by dt You can write it as like a total derivative term minus this term. This term, you know, is the flux because that's how the flux behaves. It's a square of the dipole moment. So this term becomes the short term, E short. And it can be easily seen that this is a total time derivative term, which I just mentioned briefly when I was talking about the radiation effects for eccentric orbits in GR. So that's the current state of the art. But these results have not been implemented into the waveform model. And these results have also not been used to do the resummation of modes and the resummation of radiation reaction and to obtain HLM, the wave modes as HLM quasi-circular information and HLM NQC, like eccentric modes. So this work has not been done for modes. The only result that we have so far is of the forces FR and FI in the system. Now I mentioned that they can also be like exotic objects. For example, boson stars. There is a lot of interest of doing numerical relativity simulation of boson stars because they are simpler. They are not as complicated as neutron stars, where you need to also have the equation of motion. You need to know magnetohydrodynamics. They are simpler. There is just the evolution of the scalar field and the evolution of the metric. And one might say that they can possibly be able to capture the tides because they are tidally deformable and hence can also be used to better calibrate the NR waveforms for but when we include tides in EOB. So one might possibly expect that. And these exotic compact objects is not modified GR, so you are not modifying the action, but what you are saying here is you just have a different matter field. And this matter field is now made up of the particles which are beyond standard model. So the action for boson stars is like you have the usual Ricci, and then you have where this is the scalar field or the bosonic field. Which is beyond standard model of particle physics because the mass here is different from the mass of the Higgs boson, for example. Now, when you look at this action and this action here that I wrote for the scalar field, it suggests that boson stars can be modeled exactly as scalar tensor theories. But instead of the scalar tensor parameter entering in the system from here, where I think I erased it, the scalar tensor parameter alpha being the modification of M phi, instead of it being like that. Now the modification is coming because of the presence of this scalar field here. So one is saying that from very far away, if there is like, and I am the observer here. So I'm saying from very far away, this boson star is also like a point particle. Now with the scalar charge coming because of this phi, so I can say. So boson stars, phi can be like C, and where C becomes my scalar charge. And everything now remains the same computation. We have in the PN sense, we will have this to be the diagram for gravity. Then we have this to be the diagram for the complex scalar field, and then at higher orders. But there is one complication compared to the scalar tensor model that we have. We consider it to be a massless scalar tensor theory. But here we have a potential, which is basically the mass. So the master integrals computed here in the PM sense cannot be applied here. But the EOB machinery remains the same. And the scalar tensor relation of boson stars with the scalar tensor theories remains the same. So scalar tensor theory is not only capturing the higher derivative theories like ESGB, dynamical Chern-Simons, but it is also helping us in modeling exotic objects, for example, boson stars. One can go, but the problem is the same. You can't go beyond this computation in P and PM sense. And the other thing is like boson stars are motivated from a different perspective, going beyond standard model. But if here you have like a mass, the relation between this Einstein frame and the Jordan frame is complicated. And you do not know exactly which metric you should begin with, which makes the mass term complicated. So this metric where I have the coupling of the scalar field with the gravity, I can do a canonical transformation and go from this metric to this metric where the scalar field is now coupled to matter instead of being coupled to gravity. This thing will become complicated. And yes, if for massless you can do that, for massive you cannot. And when we do this simplification of going from this theory to this theory, everything is simpler. Like the computations are easy. Here we do not know how to handle the computation. Because when we go to the Einstein frame, we can skeletonize everything, and the mass action now becomes, or the point particle mass action is simply like. And this is something that we can easily handle. Yes, but the motivation for doing both the things is. Yes, yes. And the other motivation of doing like exotic objects, for example, boson stars, could be MRIs. When you do numerical relativity simulations for MRIs, the problem is you do not know how to excise the horizon of the black hole. But if you have boson star, it is an horizonless object. You don't have to do any excision in some sense. No, test particle is a boson star because the excision of a black hole for a test particle is a difficult problem. Yes. So with this, I end my lectures today. Thank you very much.
Will be this FFR theories, which in the conformal transformation comes as mass.
Yes. Yes.
Any more questions? Thank you.